All right, so this video here, it doesn't get into a lot of detail about stuff, but it's probability and statistics. And notice here the section. It is a very brief introduction to probability and statistics. All right, so some of it's terminology, and then it's some basic graphs, very basic probability. All right, so it says, what do we mean by statistics? So informally speaking, statistics is the process of collecting data, analyzing it, and then drawing conclusions. Data is collected from a sample of a population for analysis. The collected data can be about an individual object, a variable, characteristic. The data can be discrete or continuous. Okay, so let's talk a little bit about this. So an example of data that is discrete is the number of students, say in our Math 242 class. Okay, you can count the number of students. So an example of data that is considered continuous is the collection of heights of students in our Math 242 class. You can't count the heights. Okay, so there's your discrete and continuous data. All right, and then analyzing data for quantitative data, we can use stem and leaf displays, dot plots, histograms, frequency distribution. They have the frequency distributions, relative frequency, represent the frequency of values. I'll talk more about these three when we get to each of those. I'll go into more detail. So if we have a histogram and if we smooth the histogram, the shapes can be unimodal, multimodal, or symmetric skewed. All right, so for this one, we have four graphs. We've got graph A, B, C, and D. All right, so A, just like it says here, is symmetric unimodal. B is bimodal. C is positively skewed, and D is negatively skewed. So unimodal, that means there's one hump or one peak. You can see that we just got the one there. Bimodal, that means you see how there's two peaks. Okay, the peak, like this peak right here, doesn't necessarily have to be like the highest point. You can see this point right here is higher than that one, but it's just where's there a hump and then comes back down and then there's another hump. So you can see we've got two peaks there. So that would be considered bimodal. Now this one's skewed. One term that you may have heard of on a graph being skewed, this one would be considered skewed right, and this one would be skewed left. See the humps over here, but see it's the tail here. This tail is down here on the right, and just like on this one, the tail is on the left. So we would say this one is skewed right, and this one is skewed left. All right, so for qualitative data, we can use bar graphs. They're similar to histograms, but no touch between the bars. Okay, just for categorical data. And we've got pie charts. All right, so I'll talk more about the difference between a bar graph and a histogram when we get to those. But let's look at this. We've got some data here. We've got students 1, 2, 3, 4, 5, 6, all the way to 40. And this is how many. So this would be like student number 1, student number 2, student number 3, student number 4, and so on. So instead of putting students' names here, we just represent them with a number. And so I know all the data is not listed, but you notice it says that 20 of the students are taking math, 4 of the students BME, which I'm guessing that's probably biomedical engineering, 10 of the students computer science, and 6 of the students are in electrical engineering. All right, so what we're going to do is we're going to take this data here and we're going to look at how can we represent them with pictures. All right, so we've got some examples down below, and what I'm going to do is I'm going to write that. I'm actually going to write that right here. So 20 math, 4 BME, 10 CS, and 6 EE. All right, just so we'll have it here so we can see it. All right, so what we have here on this first graph, this is a bar graph. Okay, this is a bar graph. So what it is, we have the categories here. We've got the math students, the biomed students, computer science, and electrical students. And we've got a bar here, and it just goes up to 20. You see that? And because that's how many students. This bar here goes up to 4 because there's 4, and so on. And the computer science goes up to 10, and the EE goes up to 6. Just representing it in a bar graph that we can get a picture of it. And then we have a relative frequency bar graph. So you notice here that these graphs, they look the same. But what's the difference in these graphs? Well, that's just this y-axis here. So how do we get these numbers here? Okay, how do we get those numbers? Well, the relative frequency, the way we find that is, let's just find the relative frequency for each one of these. So the relative frequency for math, so let's just write for math, the relative frequency is going to be, well, it's the number of students in math divided by the total, which is 0.5. And you can see this graph here goes to 0.5. So the biomed, that would be 4 over 40, which gives me 0.1, and that's what that goes up to, the 0.1. And then the computer science, that would be 10 over 40, which would be 0.25, and there's the height of that bar. And then the electrical, that would be 6 over 40. Let's see, 6 divided by 40, that would be 0.15, and that gives us the heights, and that's how you calculate the relative frequency. Okay. Now we have a pie chart. All right. So let me go ahead and write this down again. So we'll have it down here. 4 BME, 10 computer science, and like I said, this right here is a very brief description. It doesn't get into a lot of detail at all. All right. So here we have a pie chart. So how do we draw this pie chart? Well, I'm not going to go over how to draw the whole thing. Let's just look at, I don't know, say this piece of the pie right here, this 25%. All right, so that 25%, this is, I believe this one is the computer science one. Okay. And then, of course, this would be the math, and so on. And I'm guessing, let's see, this one's going to be the biomed. That would be B, and this one would be the electrical. All right, so let's look and see how we get this right here. Okay, so there's 10 students in computer science. So that would be 10 over 25, 10 over 40, which equals 0.25, which that is 25%. Okay, 25% of the students are in computer science. And if you notice this 0.25, this 25%, notice that's what we got up here on this relative frequency, okay? That's what it is. 25% of the students are in computer science, 50% in math, 10% in biomed, and 15% in electrical. All right. So how would we go about drawing this? How do we know how to draw this angle here? Okay. Well, to get this angle measure here, well, that's just the 0.25 times 360 degrees. And if you do the 0.25 times 360, that's going to give us 90 degrees. And that is, this angle here is 90 degrees. And then that's how you would get this one. You would do 0.15 times 360. This one you would do 0.1 times 360. And this one you would do 0.5 times 360. And this one's easy to see. That's 180 degrees there. 360 times 0.5. All right. Now, and one thing you've got to realize when you're drawing these pie charts, if you're drawing them out by hand, yeah, I mean, it's tough to say, okay, what's exactly, 90 degrees when you're over here? Or, like for this one, 0.15 times 360, that's 54, okay? Oh, I got to draw 54 degrees. It can be tough, but, you just estimate it in there. Get it as close as you can. All right. All right, so that's those types of graphs. So now let's look at some more. It says, what about continuous quantitative data? How can we represent it pictorially? We can group the data into classes and make histograms. So what we have here is we have a group of data here, all right? And what we've decided to do here is come up with some classes, 10 to 20, 20 to 30, 30 to 40, and 40 to 50. Okay, and then we come through the data here in this 10 to 20. Well, let's see. There's 1, 2. There's just 2 data values between 10 and 20. So that's where that 2 comes from. That's the frequency. Okay, and then you can look here. You can see that between 30 and 40. Well, how many is that? 1, 2, 3, 4. And so that's where that 4 comes from. Notice the parenthesis here on the 40. So that means the 40 is not included. All right. Now, they also have a relative frequency. And so how do they get this relative frequency? Well, that's the frequency for this class, which is 2, divided by, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 data values, so we divide that by 11, and that gives us the 0.18, and that's where that comes from. All right, so that's your relative frequency. It's the frequency of that class divided by however many data values you have. And let me say this. I know I went through there up top to those data values, and I counted each one of them. Okay, well, what's another way that we could get how many data values there are? Well, I could just add these numbers up here. So that's 4, 8, and 3 is 11. And so that total there is 11. So that gives me how many data values I have. And then we come over here to draw a histogram. So to draw the histogram, you see the block here, this width is 10 to 20. The width of the next one is 20 to 30, 30 to 40, 40 to 50, and so on. And so there's your width right there of each one. You see that? Now, for the class 10 to 20, What's the frequency? Well, it's 2, and so that's how high you draw the bar. You draw it to a height of 2, and then the next one's a height of 2, the next one's a height of 4, and the next one's a height of 3. Now, this is the difference. This is the difference between the histogram and a bar graph, and it stated it up there earlier. But notice in the bar graph, the bars do not touch. There's a gap between them. But in a histogram, there's no gap between the bars. Okay. All right. Now, the next one, the stem and leaf display for the given data is shown below. So here's our stem and leaf. So what we've got here is the stem and leaf. Let's just go ahead and label all that up there. So we've got a stem and we've got a leaf. And we've got 1, 2, 3, 4. Now, let me show you where that comes from. We've got numbers 12 through 41. Okay, so that's where the 1, 2, 3, and 4. We've got them in the teens, the 20s, the 30s, and the 40s. So that's the 10s, the 20s, the 30s, and the 40s. And so for the leaves, that would be 1, 3, 1, 1, 3, 4, 5, 7, 0, 0, 1. Now, where did that come from? Well, if you notice, my first data value is 12. I'm sorry. I messed that up, didn't I? That should be 2, 3. So the first data value is 12. So that's going to be, see, there's the 1, and then the 2 is right there. And then the 1, that's in the teens and the tens, and then the last digit, the 3, and so on. See, I've got 21, 21, and then I've got 33, 34, 35, 37, and then I got 40, 40, and 41. Now, this one's pretty straightforward, but in some of them, you may have a lot of data values, and the data values may not be in increasing order or decreasing order. Okay, they may not be in any order. They may just be in a random order. Well, if that's the case, go ahead and do your stem and leaf plot. Do the one, let's say like the 1, 2, 3, 4, or whatever you need to do. And then just list the leaves out here. Even though they're not in order, that's fine. But once you get finished listing those leaves, you're going to have to go back and make another stem and leaf display and put them in order. Okay? And my suggestion is, don't try to put them in order as you're reading as you're going through the numbers. Don't try to do that. Just go ahead and list them in the order that they're in, and then go back and make a second one and put them in order. It's a lot easier that way. Okay, so that's a stem and leaf display. And I know this one right here looks a lot better. I mean, it's the same one, but this one looks a lot better. And if you look at this, you can actually, if you look at this from the side, if you turn your head and look at it from the side, notice how the shape here, you see that? It looks like that histogram there. Okay, so that's pretty neat there. All right, so now we've got a dot plot. The dot plot for the given data is shown below. So we've got a bunch of data values here, 7, 3, 4, 10, 10, 7, 6, 6, and so on. So on a dot plot, you just make a number line, okay, and list all the numbers so that you can take in all the numbers. See, the lowest number we have in here is 3, and the largest is 10. So I'm going to list all the numbers between 3 and 10. And then the dot plot, so I just go through here, and let's just go through a couple of them. We got 7. So I would put a dot over the 7, and then the 3, put a dot there. The 4, I'd put a dot there. The 10, a dot there. And then we have another 10. And that's why these dots are stacked on top of each other. The dot just goes right up above it for however many you have. And then you can see I've got a 7, so I would put the 7 above that one. And then I've got a 6. And then I've got another 6. and then I've got another 7. Oh, wait a minute. That should be a 7. 7 twice, and then I'm coming to this 7. That would be a third one, and then I got 4 and 4 again. So there's that 4, and then I've got this 4, and so on. And you would just, keep going until you plotted all the dots. I think you probably get how to do it now. All right, so that is, like I said, a very brief and quick description of some ways that we can represent data graphically. Okay, like I said, it was not a lot of detail. I know that. That's not really the intent of this course, to get into a lot of detail on that stuff. All right, so let's look at some basic terminology. It says an experiment is a planned activity or process. For example, tossing a coin is an experiment. Outcomes, the results of an experiment, are known as outcomes. In our experiment of tossing a coin, the possible outcomes are heads or tails. So you're doing an experiment of flipping a coin, and when you flip the coin, there's only 2 possible outcomes. You can either get heads or you can get tails. Then the sample space for an experiment is the set of all possible outcomes of the experiment. So in the example of flipping the coin one time, all of the possible outcomes that we can have is we can have a heads or we can have tails. So in this case, the sample space would be HT, heads or tails. And whenever we're representing a sample space, we typically use the capital letter S. Okay. So now it says, let's now consider the experiment to be tossing a coin 3 times. Determine the sample space. All right. So when we look at this, when we're flipping a coin 3 times, when we look at this, well, the sample space could be, we could get heads, heads, heads. We could get heads, heads, tails, and so on. And you would have to list all the possible combinations you have there. And then we could have maybe heads, tails, heads, and so on. And, probably end up with tails, tails, tails as the last one. All right. And I know flipping a coin 3 times, it wouldn't be that difficult to come up with all the different possibilities, but it would be easy to miss one. So one of the things that we can do is we can draw a tree diagram. And that's a way that we can get the sample space really easy, is using a tree diagram. So let's draw a tree diagram here. Let's see, maybe come here. All right. So when I toss the coin 1 time, I'm either going to get heads or I'm going to get tails. This right here is the first flip. And then I'll toss a coin the second time. And when I toss it the second time, I'm either going to get heads or tails. All right. So that is, say, like on the first flip, I get a heads, and then I flip it again, I'm either going to get a heads or a tail. So this one right here would be considered the second flip. Now, if I flipped it the first time and I got a tails, then from here, I can either get heads or tails. All right. And then we're going to go flip it a third time. So if I flip and get a heads on the first one and then a heads on the second one, then on the third flip, I'm either going to get heads or tails. See, this is the third flip. Well, instead of that, on the first flip, I could get a heads. On the second flip, I could get tails. And then on the third flip, I'm either going to get heads or tails. And then the same thing here. I could get tails, heads, and then on the third one, I would get heads or tails. And then on this one, that would be heads or tails. And so what we have here is this gives you all the possible outcomes. See, I could get heads, heads, heads. I could get heads, heads, tails. Heads, tails, head. Heads, tails, tails. And then the rest of them, that's this. And then I could get tail, head, tail, 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 head, and tail, tail, tail. So this is my sample space. I could get this. All I'm doing now is just writing these down for my sample space. And you can see we got 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. This is my sample space. Okay. All right. So now let's keep going. It says an event is a subset of the outcomes contained in the sample space. That's an event. So in the experiment of tossing a coin 3 times, the event of getting exactly 2 heads when flipping a coin 3 times. So I'm going to represent this with the letter E for the event, and the event is getting exactly 2 heads. All right, so this is the good part about writing out your sample space when you can, because if you write your sample space out, everything's right there. So what do I want? I want exactly 2 heads. So what is that? There's one with exactly 2 heads. There's one with exactly 2 heads. And there's one with exactly 2 heads. So this event is H, H, T, H, T, H, and T, H, H. So there's my event of getting exactly 3 heads. And then a simple event is an event that has only one outcome. And here's an example. So in other words, what would the event be of getting all heads? Well, it's just this one. See, it's just this one right here. It just has one outcome. And so that would be considered a simple event. All right, so next we'll introduce the concept of probability. Okay. The connection between statistics and probability is the following. Probability is used to measure how confident we can be in the conclusions we draw after analyzing our data. So the probability of an event is the likelihood of an event happening. The probability of any event lies between 0 and 1. That is really, really important there. If you're calculating a probability and you get an answer more than 1, that's larger than 1, then you did something wrong. Okay? All your probabilities are going to be between 0 and 1. And yes, they can equal 0 and they can equal 1. And just like it says here, with 0 corresponding to the event not happening and 1 corresponding to the event always happening. Okay. And then if P of X denotes the probability of X, then the probability of X is greater than or equal to 0, and the sum of all X, or the probability of X, is equal to 1. This note here, the total probability must add up to 1, and probability can never lie outside the range of 0 to 1. So if you're taking all the probabilities of you have a sample space and you're taking all the different probabilities, you cannot have, it's not gonna ever be larger than 1. They're all gonna add up to 1. All right. So in our experiment of tossing the coin 3 times, the probability of the event getting exactly 2 heads would be. All right, so now notice that there's a difference here in what they're asking in this question here and that other question. So this one, it says, what is the event of getting exactly 2 heads? So if they're asking you for the event, they're asking you for the set. Okay, just like this right here. But when they ask you for the probability, so let's look at that. The probability, and before we find it, let's go ahead and look at this statement right here. For an experiment with equally likely outcomes, the probability of event A is just the number of outcomes in event A divided by the total number of outcomes in sample space A. Another way that you can look at it is you could look at it as successful outcomes over possible outcomes. Okay, that's probability. It's the number of successful outcomes divided by the number of possible outcomes. So let's come back up here to this, and let's find the probability of getting exactly 2 heads, and I'll use the letter E because that's what E represents in the problem. It represents the event of getting exactly 2 heads. So if I look at this, the probability of getting exactly 2 heads, well, I need the number of successful outcomes. Well, there's what? 1, 2, 3 of them. You see that? That's all the different ways that we can get exactly 2 heads. There's 1, 2, 3. So that's the number of successful outcomes divided by the number of possible outcomes. Well, where are the number of possible outcomes? That's how many outcomes are in the sample space up here. And how many were there? 8. And so that's 0.375 is your probability. Okay. All right, so now we've got some definitions. It says the complement of an event A is the set of all outcomes in the sample space S that are not in A. It is denoted A prime or A with the superscript C. This right here is the 2 different ways that you might see a complement represented. Okay, if you see one of those, then you know that's what that means. All right, and then we have the union event of events A and B, denoted by A union B is the event consisting of all outcomes that are either in A or in B or in both. And then the intersection of events A and B, denoted A intersect B, is the event consisting of outcomes that are both in A and B. It's basically what they have in common. So intersection, that's what they have in common. And union, that's everything in A plus everything in B combined into one set. Now, that's really about the extent that we get into with union, intersection, and complement. If you want to understand it more and see a little bit more about it, go search my YouTube channel. Search for sets, union, intersection, complement. I've got a video on doing that with those sets. Goes into quite a bit of detail on it. So check that out if you want to see that. And then we have some useful probability basics. So the probability of the complement is just 1 minus the probability of A. So the probability of A complement is 1 minus the probability of A. And that makes sense. So let's just go back up here to this probability here, right here. Well, what if we wanted to find the probability of E complement? All right, so that would be what? What's the complement of E? So what would be the complement of exactly 2 heads? Okay, well, not exactly 2 heads, right? So what would that be? Well, by that rule, that's 1 minus the probability of E, which is 1 minus 3/8, which is 5/8. Okay, so the probability of not getting exactly 2 heads is 5/8. And if you look at that, well, let's look at it. Where we don't have exactly 2 heads. Well, that's what? This one, you see that? 1, 2, 3, 4, 5. And that's all they're talking about there. All right, and then we have the probability of the union of two events is the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. And before we read the next one, let's go back up here to this definition. It says if events A and B have no overlap, in other words, they have nothing in common, we say that they are mutually exclusive or disjoint events. And events A and B are said to be independent if the event B has no effect on the outcome of A and vice versa. So mutually exclusive and disjoint, I think that makes pretty good sense there. That's, they have nothing in common. Okay, that's all it means. And then events A and B to be independent. Okay, so let's go back up to flipping the coin. Let's talk about that. So let's say I have a coin, and so I take the coin and I flip it, and it lands on say heads, and I record heads. And then I'm going to flip it again. So I pick the coin up, I flip it again, and let's say it lands on tails. Okay, so let me ask you this. When I flipped the coin the second time, did what happened on the first flip, did it affect the second flip? No. So they're independent events. Okay? And if A and B are mutually exclusive, then the intersection of probability of A intersect B is equal to 0. And all they're telling you there is they're modifying this formula here. And what they're saying is if you have two events and they're mutually exclusive, then you're not going to have this part of the formula. Say when you have probability of A union B, because this right here is just going to go to 0 if they're mutually exclusive. And then if A and B are independent events, then the probability of A and B is just probability of A times probability of B. You can multiply them together. Okay? That's if they're independent. All right, and then now let's come up here and we're just going to do the first part of chapter 2 here. It's not a lot, just talk about it a little bit. So random variables. A random variable is a function that associates a unique numerical value to each outcome in the sample space of an experiment. Random variables are usually denoted with capital letters such as X, Y, etc. There are two types of numerical random variables commonly used in statistics. These are discrete random variables. Okay, one is discrete random variables. These random variables take on countable numerical values. For example, let X equal the number of students in a class. Since we can count the number of students in a classroom, X is a discrete random variable. All right, I had to pause the video. My weather radio went off. I don't know if you heard it there at first, but it's gone. It's off now. So that was a discrete random variable. And a discrete random variable that takes only two values is called a Bernoulli random variable. So we'll talk more about that later on, where we have two outcomes. We'll talk more about, that's like a success or failure with two outcomes. It either happens or it doesn't. And then we have a continuous random variables. These random variables take on values that are uncountable and adhere to the following. The values of a continuous random variable can be any value along a line interval, including values between any two values. Okay, so you're getting there into stuff like how much does somebody weigh or their height and something like that. When we're talking about continuous random variable, you're not going to be able to count it. And then the probability of X equals C is 0 for any value of C. So that's for the continuous random variable. So, for example, let X equal the heights of the students in inches in a particular class, we measure heights rather than counting heights. Also, the probability of height being exactly equal to a particular value is 0. Okay, so that ends the lesson for this one. The next lesson will start here on section 2.2, discrete. Talk about discrete random variables more. Probability, discrete probability mass function. We'll talk about some other things. But like I said, that's just a very brief kind of skim the surface of some stuff in statistics. It doesn't get into a lot of detail, so we'll get into more detail later on in the class. But for this, that's really about, as far as we go into this. So hope the video helped, and like I said, check out the other videos. I got some that go into more detail about these specific topics if you want to look at those. All right, see you later.